very useful. Next, Fubini theorem only deals with rectangles, but we have to study integral over general Jordan domain. Okay, so at the beginning of today's lecture, we prove an important theorem saying that a function defined over a Jordan domain is integrable if and only if, not if and only if the discontinuity set has Jordan contains 0. Okay, so Jordan domain is quite natural in the discussion of our integral. Our integral is in the sense of Riemann integral. In the future, we will study the Lebesgue integral. That is another story. But for Riemann integral, we are studying in calculus. The Jordan domain is very natural. Okay, but we have to go beyond the category of rectangle. So we need to study more general Jordan domain. Okay, so the Jordan domain we will consider is the so-called simple domain. Okay, simple domain. What's a simple domain? Roughly speaking, simple domain is the domain bounded by a graph of continuous function. So, for example, this is the x-axis, this is the y, and then we have a function y equal phi plus x, and we also have another function y equal phi minus x. Both phi plus and phi minus are continuous function over a lower dimensional part. In our notation is u. Then the boundary this domain bounded by y, the graph of y equal phi plus x and y equal phi minus x. If phi plus and phi minus are regular enough, for example, they are continuous. Actually, if they are integrable, it's okay. But to simplify our notation argument, we only consider the case that they are continuous. So this is the so-called Jordan domain. Okay. Of course, this is a two-dimensional example. This idea can be generalized to higher dimensional case. So, we give a definition. Let U is a subset of n minus 1. This is compact, sequentially compact. That is bounded and closed. We simply call compact. In general, the concept of compact is defined using open covering, but we have not discussed open cover theorem. So we only study the sequentially compact. But in Euclidean space, sequentially compact and the compact in the sense of cover, open cover, are equivalent. So I simply call compact. That is sequentially compact. Okay. So U is a compact, sequentially compact subset of Rn minus 1. And then phi plus and phi minus is a function defined on U is continuous. Okay. In fact, the integrable is enough. Okay. So, but we for simplicity, we require them to be continuous, and also phi minus not greater than phi plus. Then such a domain D, such a subset D, UT, U belongs to the U, and T belongs to the interval. A subset of Rn, because U in D sorry, u, small u in capital U is n minus 1 dimensional. Therefore, this small u has n minus 1 coordinate and another coordinate d. Therefore, the points in D has n coordinates. So this is a subset of Rn, a subset of Rn. So this subset of Rn of this form is called a simple domain. Okay, in Rn. Simple domain in Rn. Okay. So in our this picture, if we consider the horizontal axis to be Rn minus 1, and the vertical is the last dimension. Okay, so this is the simple domain. So this is the motivation to define simple domain. Simple domain is very good for for taking integral. We have the lemma. Let D be a simple domain. Then D is a compact and roll down. D is a roll down domain. Therefore, continuous function over D is integrable. Okay, so we will study how to compute the integral of continuous function over D. But first, we need to describe the proof of this theorem, this lemma, to ensure that D is a roll down domain. Okay, so since U is compact, U is closed and bounded. So it is easy to see that phi. I need to write proof. Then U is closed and bounded. That is compact. Then phi as a continuous function defined over sequentially compact set. So it's bounded. Are bounded. Okay, these two functions are bounded. So because the phi is bounded and the U is also bounded, it is easy to see that the set D is bounded. Okay, D is bounded. So our conclusion is that D is compact, that is bounded and closed. So we already know that D is bounded because phi plus and phi minus are bounded. So it is easy to see that D is bounded. Now we need to prove that it is closed. So to prove that D is closed, take a sequence UK and TK in D, and UK TK converge to a point UT. The question is that does UT belongs to D? If whenever UKTK is a sequence in D and it converges to a point UT, you have UT belongs to D, then D is D is closed. This is the definition of a closed set. So we can prove that D is closed. Why D is closed? Why UT belongs to D? So to prove D is closed, we need UT to belongs to D. But why UT belongs to D? So UKTK belongs to D means that UK belongs to U. And UK converts to U because UKTK converts to UT. Okay, but U is closed. Our U is also compact. That is, U is bounded and closed. So this implies that U belongs to U. Okay, and UKTK belongs to D means that TK belongs to phi uk, phi minus uk, phi plus uk. Okay? Or in other words, phi minus uk not greater than tk, not greater than phi plus uk. Now phi plus and phi minus are continuous, so the left hand side converges to phi minus u, okay, because uk converges to u, and the right hand side converges to phi plus u, and also tk converges to t. So using this inequality, the three terms in this inequality, phi minus uk, tk, and phi plus uk, all has limit. All these three terms in this inequality converge. So the limit kept the relation. By the property of limit of convergence, we see that t belongs to phi minus u, phi plus u. So u belongs to capital U, and t belongs to the interval of the value of phi minus and phi plus in u. Therefore, by the definition of D, we conclude that ut belongs to D. So D is closed. Okay. So we still need to prove that D is a Jordan domain. Okay. So to verify that D is a Jordan domain, previously we have a theorem saying that a domain is, by the definition of a Jordan domain, a subset is a Jordan domain if its boundary has Jordan content 0. So from this picture, intuitively, you will see that the boundary of D consists of 4 parts. The first part is the upper boundary, the graph of phi plus. But the phi plus is a continuous function. Its graph is Jordan content 0. Okay. Similarly, the lower boundary of D is the graph of phi minus. It is also a graph of a continuous function. Therefore, also has Jordan content 0. Okay. And what's the vertical part of the boundary? I left this as an exercise for you to prove that the vertical part is how to write the vertical part? The vertical part is denoted by sigma 0 and the upper part sigma plus and this part sigma minus. Okay, so the sigma 0, sigma plus, and the sigma minus are graph of continuous function. And how about sigma 0? Sigma 0, the projection of sigma 0 in Rn minus 1. In this picture is this 2 is the endpoint of U, but in higher dimension, they are the boundary of U. Okay, so I will write sigma 0 for you in the next page. Sigma 0 is x of the form ut, where the u part belongs to the boundary of U, and the t part belongs to the value of you can check the sigma 0 is this set. But this set, since U is Jordan domain, the boundary of U has Jordan content 0. So the boundary of U has Jordan content 0. Then you can prove that sigma, the boundary of U has Jordan content 0 as a subset of Rn. Then sigma 0, you can prove, this is an exercise, you can prove that sigma 0 has Jordan domain, Jordan content 0, but sigma 0 is a subset of Rn plus 1. our notation. The U is n minus 1. So the boundary of U is also Jordan contain 0 set in n minus 1. And our sigma 0 is a subset of Rn, has Jordan contain 0. This I left for you as an exercise.